Okay, so welcome everyone to Clean Coder. So today we are going to solve problem number 144, binary tree pre-order traversal. So it's a easy lead code problem. Let's go through the problem statement quickly. So what they tell is that given the root of a binary tree, we are supposed to return the pre-order traversal of its node values. So this is the sample tree. So pre-order traversal is in the form root left right. Okay, so this order we need to maintain recursively. So the output for this sample tree would be 1. This is the root, then left, there is no left, then right, then this root 2, then there is left 3. So the output would be 1, 2, 3. We'll take a look at an little big example also. So let's see the constraints. So the number of nodes in the tree are in the range 0 to 100. Okay. And node values are between -100 to +100. Cool. They have also given a follow-up question. Recursive solution is trivial. Could you do it iteratively? Yeah, iterative solution is actually a little like it forces you to think. Like recursive solution is straightforward. So let's move to our whiteboard. So let's analyze the problem. So there are two solution approaches possible, right? First one is the recursive one, which is, I'll say, trivial. Okay, so what we can do in recursive solution is that we'll keep the print statement before left recursive call and right recursive call. So it will print the output in pre-order traversal fashion. So this is like quite straightforward. Let's take a look at the iterative solution, which is like a little, I'll say, challenging, or like it forces us to think a bit. So in the interest of time, I have written the iterative solution well in advance. Like, feel free to pause the video if you want to think a bit about the iterative solution. So let's analyze the iterative solution with this test case. Okay, so this is the sample tree I have taken. So this is the complete binary tree, and its pre-order traversal should be like this. So let's try run this binary tree on this code, and let's see what is our output, and we can compare it with the correct output. Let's start. Let's start line by line. So assuming this is the root of the binary tree passed to us. Okay, so we are making a list since output is expected to be a list. So that's why we are doing this. This is the base type condition. So this is the stack we are taking, stack of tree nodes. Okay, let's take a stack. So what we are doing is we are doing a while root is not equal to null. If root dot right doesn't exist, like if root dot right is not null, then we need to push that in stack. Okay, so in case of 1, root dot right exists, so we need to push 3 in stack. And what we are supposed to do then, answer dot add, answer is a list, answer dot add root dot value. So root dot value is 1, so we'll print 1 here. Okay, so now we need to move to the left subtree. Okay, so our pointer would move to 2 now. So root is not null still, so we'll just move in the next iteration of the while loop. So it says if root.write is not null, again 2's right child is not null, so we are going to push 5 into the stack, and we are going to print 2 in the output, and let's move to the left child. Okay, so we are at 4. Now root is still null, so this if a block would still not execute, and let's move to the next iteration of the while loop. So root.write is not null, actually 4's right child is null, so this if won't execute. Now answer.add root.value 4 we are going to add in the output. Okay, and we are going to move to the left child of 4. So left child of 4 is null, so now our root is pointing to null. Okay, the root is pointing here now. So this if block would execute now. What it says, if root is null, okay, if stack is empty, stack is not empty now, so this condition won't execute. It says root is stack.pop, so I need to pop an item from the stack, so I'll pop 5 and assign root there. Okay, so let me pop 5 first. Okay, and let me assign root from null to 5. Okay, so 5 points here now. And now we are towards the next iteration of the while loop. So it says if root.write is not null, but root.write is null, so we need to add answer in this list. So 5 would be in the output list, and root.left, so again 5's left child is null, and my root pointer would move to null. Okay, so now root is null, stack is still not empty, and root would point to stack.pop, which is 3 now. So let me point our root to 3. At this moment stack is empty actually, so our root would point here. Let's move to the next iteration of while loop since root is not null. So if root.write is not equal to null, which is not null, we need to push 7 to stack. Okay, and we'll add 3 to our answer. Cool, and we'll move to the left child of 3. Left child of 3 is 6, so we are here. Okay, so at this moment root is not null, so let's move to the next iteration. Root.write is null now, so this won't execute. Answer 6 would be added to the answer list, and we'll move to the left child of 6, which is null. Let me point it to null now. So root is pointing to null now. So now this if block would execute, and since our stack is not empty, so this break condition won't execute, and root would be stack.top. So root would be pointing to 7 now. Let me make that change quickly. Let's pop 7 from here, and root pointer would be pointing to 7 now. Okay, so now let's move to the next iteration. So root dot write is null, this won't execute. Answer dot add root dot val, so 7 would be added to the answer list. And root is root dot left, root dot left is null, so root point here. Now root pointer is null and stack is also empty, so at this moment this condition would execute and it will break out of this while block. So this is our output list which we need to return, and it matches with the expected output. So this is the correct solution, I believe. So let's quickly discuss the time and space complexity also for both the solutions, recursive and iterative. So for recursive solution, time complexity is quite straightforward. It is O of n, since we are visiting each node exactly once, and space complexity would be proportional to O of log n, because we are using a function called stacks which also takes memory. So in case of iterative solution, time complexity is straightforward, big O of O n, because we are visiting each node once, and space complexity would also be O of log n, like this is proportional to the height of the binary tree. And you can notice that at any moment we don't add items more than the height of the binary tree in this stack, so space complexity is proportional to O of log of n. I assume that you liked this sort of explanation of this simple problem. So if this explanation helped you in any way, please subscribe to my channel and please like this video for similar content. So thanks a lot for watching.